Welcome to Ask and Learn.
We're asked to prove that M and M bar accept the same language in part A. So, first, let X be a string accepted by the machine M, and let Sx be the state where the string ends in X. The string X ends in machine M. Now, we know that X is accepted by M, so it follows that Sx is a final state of M. And by the construction of M bar, it follows that X will end at the state Sx, the equivalence class containing Sx, this is the R star equivalence class containing Sx in M bar. And we have that the R star equivalence class of Sx is a final state, since all states in the R star equivalence class of Sx are final states. Now, this is because Sx, which is in the equivalence class of R star containing X, is a final state, so it follows all the other states in R star of Sx by previous problem are all final or non-final states. So it follows that the R star equivalence class containing Sx is a final state in M bar. This implies that M and M bar accept the same language. Now in part B, we're asked to prove that if the machine M has the property f of S0 x equals S for all states S and some string in I star, then M bar, the machine, has the minimum number of states of all finite state automaton equivalent to M. So, to prove this statement, suppose that M has the property f of s naught x equals s for all states s and m, and some string x in I star this should be written as M has the property that for all states S in M, there is an X in I star such that this statement, f of s not X equals S, is true. So suppose that's true. And now let N be a finite state automaton equivalent to M. That has the minimum number of states. We know this exists because the number of states is a positive integer, which we know is bounded below and by the well-ordering property of the natural numbers must have a least element. Now, because n has the minimum number of states, it follows that n bar has to be equal to n. Otherwise, n bar would have less states than n, but n bar would still recognize the same language and thus be equivalent to n, and therefore equivalent to m. But then n bar would have less, would be the new minimum, which is a contradiction. So, since n bar recognizes the same language as n, recognizes the same language as m, and therefore recognizes the same language as m bar. And they both have equivalence classes as their states. So the states of n bar form a refinement of the states of m bar. Now, there are no empty equivalence classes in M bar. Because we have that for all states S, there is a string x and I star such that f of s0 x is equal to s. And therefore, since there are no empty equivalence classes of M bar, it follows that the states of M bar form a refinement of the states of N bar. By a previous exercise. However, this implies that the states of N bar and M bar must be the same. Therefore, it follows that M bar has the minimum number of states. For any finite automaton equivalent to M.